Hello everyone, welcome to another video of From Concept to Circuit. In this video, we are going to make a FM receiver using our ADALM Pluto. First, we'll see how we can receive and demodulate an FM signal and what is the signal composition after demodulation. Then, once we went over the fundamentals of FM demodulation, we'll go and implement a Python code to make a make our receiver using ADAM Pluto. Finally, we tune in into a local radio and listen to the station. Okay, now the outline. So as always, using ADAM Pluto first, we need to configure it. Uh, the RF bandwidth, the sampling rate, and these types of things that we talked about in the previous videos. Then we need to make data acquisition, and it should be an IQ data acquisition, so we get access to the phase of the received signal. For FM demodulation, we just extract that phase and differentiate it. Uh, Using differentiation, what we do is that we extract the phase information of that FM signal, and that is our data. We'll talk about this later. Then, because that signal usually is 200 kilohertz, because that's the bandwidth of a, uh FM channel, we need to do some digital filterings to avoid aliasing, and also there is another concept that we need to know, which is the emphasis. I'll talk about that. And finally, because now we want to send the data to the speaker to play it, we need to make the data from the high sampling rate we had initially from ADAM Pluto to the sampling rate of the audio. Usually, for instance, we can use 48 kilohertz. So that's a decimation requirement. That's for that we need to do decimation. So as always, we need to, for our SCR configuration, we need to set an LO frequency for our RX. I tuning some of the RX LO frequencies. I came to know, like for instance, in my area, I can get one station around this, but this is basically the station that you want to tune in. Then you need to choose a sample rate. Usually, because the FM bandwidth is around 200 kilohertz, you need to be maybe 5 times or 10 times of that, so you get all the signal information when you are sampling the signal. Uh, yeah, as I mentioned, for RF bandwidth, usually FM each FM channel is 200 kilohertz separated from each other. So usually the bandwidth is 200 kilohertz, and we can set the RF bandwidth to be that. Then using SDR-RX, we can uh, read the data, right? Once we read the data, we need to perform some process to demodulate it. Basically, I just shown here the equations for FM radio. For FM modulation, the data, which is here M, is integrated and added to the carrier of our signal, to the phase of the carrier of our signal, right? So our signal becomes a cosine of omega carrier T plus delta omega integral of m phi d phi, if right. So here basically this is our FM modulator. If we want to demodulate it at the receiver, what we need to do is, as you know, uh, at the receiver we usually can, in ADAM Pluto, we can easily just get the phase of the received data, which is this part, right? Which is omega uh, phi is omega ct plus this term, right? So we just need to make a derivative of this to remove the integration and come up with this, which is just 1 2 pi omega c plus delta omega mt. And this is our data. Also, because we are using ADAM Pluto and our RXLO is already tuned in at the carrier frequency, because we are multiplying the received data, we down mixing it by omega c, we basically don't have even this term. We just have, for the phase, we just have this term as the phase. I just shown it here. our received data at the input of the baseband data at the input of ADC is A e by power of j delta omega integration of m phi d phi, right? Tau, you can say tau or phi, m tau d tau, right? So here, what we first of all, we don't need this amplitude, right? We can just normalize to remove this, right? Then here we have this phase. We just need to do NP. If the data is in a numpy array, we just get the angle, which is this term, delta omega integral of m tau d tau. Then we take the derivative of it, right? And that will give us our FM signal, right? One other thing is that because usually the angle is a wrapped angle, meaning that it usually gives you some the information from minus pi to plus pi. So if you have, for instance, if you have data, let's say if, which is higher than pi, it will wrap it around to make it be in the range of minus pi to plus pi, right? This may cause a discontinuity in our receiver. So that's why we need to unwrap it so we get the raw phase information so it's not wrapped between minus pi to plus pi. That that also we need to do. After differentiation, we need to unwrap the phase. And now we have the FM demodulated data, right? Now let's talk about, okay, now that we have that M, we want to see what is the composition of M. M is a 200, you can say it's a 200 kilohertz. It has a bandwidth of 200 kilohertz. And if I just want to briefly say what is the composition, if the channel is a stereo radio, it means that they need to broadcast the left information, the sound that is played at the left speaker, and also the sound at the right speaker. So when you want to make a stereo uh, play, you play L to the left speaker and R to right. The way they do it is in the baseband near DC without any carrier tone of empty, they create L plus R. Then they put L minus R, which is the other uh, term, uh, at uh, at the frequency offset of 38 kilohertz. And the way they indicate that the channel uh, is a stereo channel is they put a pilot tone at 19 kilohertz. So when the radio sees there is a pilot tone at 19 kilohertz, they they know that twice of that with an offset twice of that pilot tone, which is 38 kilohertz, there would be L minus R data, which is another term for a stereo transmission. Okay, and we'll see that actually in our spectrum when we run the code. Also, there is another thing that some of the radios add, which is RDS. This is we don't. This is an optional digital modulation which shows that a station information. I think you saw this when you in your car you tune into an FM radio. They show the sound, the song that is now being played, or the information of the station, etc. Right? And then once we have this, let's say we find a way, first we detect the pilot, then we find a way to find L plus R, then we find a way to find L minus R. We just, what we do is we just, by these terms, by adding them and dividing them by 2 or subtracting them and dividing them by 2, we find out L and R, right? For this video, because we don't want to make this video very long, we go over the first step, which is just extracting L plus R, um, meaning that we just extract the mono information, just one mono data. And the way we do it is that basically we just take the whole signal, we take the whole empty, add a filter, and then send it to the speaker, right? So the 38 kilohertz or the 19 kilohertz will be attenuated, and also because when they go to the speaker, they are out of the audible range, you don't hear them. But in the next video, we'll go over now to make the stereo extraction, first detecting the pilot tone and then extracting the other term. Okay, now that we have M, what we need to do is also we need to because M, as I showed, is originally if I set the Pluto SDR sample rate to be 1 megasample per second, its sample rate is different from the 48 kilohertz that I want to send to the speakers, right? So I need to do some decimation, but uh, but for that, what I do is that before doing the decimation, because when I do the decimation, if there are some uh, tones higher than the final decimated frequency, they will fold back to the main spectrum and they may cause SNR degradation. So what I do is that I filter to remove all the unnecessary noise that is in the band, then I decimate the signal. I do this for just using an FIR filter, right? Another concept is de-emphasis filter, which is basically applying a one-pole low-pass filter. But for North America, it should be 75 microsecond time constant. It depends on the region of the FM radio. But what is this? Let me talk about this a little bit. As you know, one thing is that when the transmitter wants to transmit the data, uh, higher frequency information might be weaker uh, compared to lower frequency information. And that means that they might be more prone to noise. So when the noise is added to that part of the spectrum, it may cause more SNR degradation because S, which is the signal power, is lower in that region. So what they do usually in the FM transmitters that are across the town, when they want to transmit the radio, they apply a pre-emphasis signal boost, meaning that they add a high pass filter, they apply a high pass filter to the data, so the the lower frequency information gets a little not attenuated, but basically you can say the higher frequency information gets a boost, so its signal power increases, making it uh, less susceptible to SNR degradation in presence of noise. But when you receive this and demodulate it at the receiver, you don't need this anymore because it has added some effect to your data, which may um, not may cause a signal quality reduction. So what you need to do is apply a reverse of this high pass filter, which is here a low pass filter, to reverse that effect. And that is the one that we need to do, which is a de-emphasis filter. And it's a very simple one pole filter with its time constant depending on the region that the radio is being transmitted in. Finally, once everything is done, we need to decimate the data to the sample rate that we want. For instance, if the sample rate, SDR sample rate was 2.4 megahertz and we want to make it 48 kilohertz, we first find the decimation factor, then decimate the signal. For instance, if this is 50, we just take every 50th of the data uh, to make it a lower sample rate. And we then send this to the speakers. Okay, so this is a summary of how we can implement our FM receiver. Now let's go to the code and see how it's done there. Okay, now let's look at the implementation in Python. First, as always, as you could see in the previous videos, we connect to our STR ADALM Pluto 8 with just ADI.AD9361, giving the IP address to it. Then we set the STR RxLO. I found this frequency by just doing some fine tuning. This one thing to note here is that I'm using the ADALM Pluto with the default crystal that comes with the package, and that crystal is not a very robust crystal, reference crystal that creates the 40 megahertz reference signal for us. Therefore, this 103.55 megahertz might not exactly be this frequency when I measure the RX LO. There might be a little offset to this, and also that crystal may change due to temperature. The frequency of that crystal may change due to temperature and other factors that may also cause another frequency shift, causing another offset. But for this video, we are using the very basic um, setting of ADALM Pluto, not adding any extra circuitry or any amplifier or etc. Just using bare ADALM Pluto. Then the sample rate, I set it to 1 megahertz because I wanted to take more information of 200 kilohertz channel bandwidth, which I set to RX, which I set in RX RF bandwidth. The buffer size, and one other thing is the gain control mode. I set it to a slow because this time, because we are tuning into an actual radio, we want the VGA to uh, control the gain, so we receive a very steady signal at the mixer input. So I set this to so it tracks the signal amplitude and always tries to keep it at some level. Then here we define some variables such as audio sample rate. The decimation factor is calculated here. The FIR filter tabs for anti-aliasing is calculated here. Then the de-emphasis low pass filter coefficients are also calculated here. A very simple one pole low pass filter with tau of 75 microsecond. One last thing before sending the data to a speaker is I added a low pass filter with 15 kilohertz to further attenuate any noise we have in the line before sending it to the speaker. Then our main buffer arrays and uh, threadings. I use threading because I wanted to make the plotting, because I have a plot that shows the spectrum of the FM signal, uh, uh, the received signal. So I wanted to put them in different threads so it doesn't take a lot of time from the main processing thread to plot the data, because that thread is important to be very, it needs to be very quick, because before the RX buffer gets overflowed, so the data, it doesn't receive any more data, you need to go and read it back again. So your process needs to be quick. Then the FM demodulation, basically I first normalize the received data in this function. And as we saw in our demodulation, let me show here. Okay. So these equations, first we normalize, then we are when we normalize, we have e by power of j delta omega integral of m tau d tau. The phase of this is basically this one. So we just need to take the angle. Then to find m, we just need to take a derivative of that phase. But also we need to unwrap it, because as I mentioned, the angle, if you don't unwrap it, it wants to make it from -5 to 5, which may cause some discontinuity. And that's it. That's our FM demodulator function. In the main thread, what I do is basically I first read the strrx buffer by using str.rx. I copy it into IQ samples. Then I go here and demodulate the information using the FM demodulator. Then I use a low pass filter that before decimation to avoid any aliasing. Then decimate the filtered data here using the coefficients that I calculated. Sorry, the decimate I decimated using the decimation factor. For these FIR tabs, I calculated these FIR tabs top of the code. Then I apply the de-emphasis filter, low pass de-emphasis filter here. And now after that, I just have my data. That would be my data, and I just put it in my audio buffer. And basically, what I need to do is that I just need to stream out that audio buffer to the speaker using other threadings. I also calculate the spectrum of the received data to show you the composition of the spectrum. Uh, okay, the rest of the code is how to play the received data using the speaker, and also the Qt plot to show the spectrum, which I'm not going to go over to make the video longer. This is the main FM demodulation here. That was essentially what we were interested in. As I mentioned earlier, this is implementation of receiving mono information. And in the next video, we are going to see how we can use the pilot tone and also extract the stereo information. Now let's run the code and see how is it receiving the information. Okay, let's run the code and see how it receives FM. Uh, to avoid getting copyright because there are sounds being played in the station, I just try to add some artifact, but I just want to you see how is the quality of the received data. And then I mute it and I talk over the spectrum. You can see the setup. I'm just using a very simple setup of ADALM Pluto with the uh, antenna that comes in the package, and it's in indoor test behind the window. So and there is no amplifier in the chain. So just the antenna, which is I don't think it's a very optimized antenna for FM receiver, and then the ADALM Pluto by itself. 1035. Okay. Now that we saw how is the quality of the received data, I just want to mention something about the spectrum that we also go over in the future videos. As I mentioned in the beginning of the video, uh, if the channel is right now, I'm just showing this spectrum because I set it to be for mono. It's just showing up to 24, which is just a Nyquist of the 48 kilohertz that is going to the speaker. But basically, one thing you can see here is this pilot tone around 19 kilohertz. It's definitely because of the frequency mismatch that I talked about earlier. It's not exactly 19 kilohertz, but you can see there is a very obvious pilot tone here, which is an indicator that this station is transmitting a stereo. Therefore, we can use this pilot tone and lock to 30 kilohertz, which is twice of this frequency, to extract the other information at around 38 kilohertz, which is L minus R, because I talked about having L plus R before the pilot. In the future videos, we talk about how we can extract that, so we can extract L and R and receive the stereo information. But that's for another video. I don't want to make this video longer. Thank you for watching this video. Please in the comment give me feedback on what you want to see, what are your interests, and also share this with anyone that you think might be interested, and help us grow the channel. I really appreciate it. Uh, Thank you.